All right, welcome back. We are going to talk about something called concavity, which is a basic way to describe the curvature of a function. So I'm going to try to cram in a bunch of information here so you can pause it and kind of reflect on it as we go. So concavity, let me give you a couple examples. If you have a curve that opens up, not specifically because I drew up arrows, but this is what we call concave up versus something that curves kind of down. We call that concave down. And something that has no curvature, like a line, doesn't have concavity. But the tricky thing is if you have some function like maybe like a sine curve, or you have a polynomial like a cubic, or even fourth power, fifth power, it has all these changes in direction. The concavity is changing throughout the function. So this green portion, this is all concave down. But if I switch to red, this is concave up. And then somewhere there's a moment in here where it switches back to concave down. And that moment is actually called the point of inflection. Many functions don't have a point of inflection if there's no change in concavity. For instance, this parabola up here is always concave up, so it actually doesn't have a point of inflection. This line doesn't have concavity, so it can't have a point of inflection. So we're going to talk about this a little bit right now and how it's tied to calculus. So just a quick recap of f and f prime. When you're analyzing the function f, remember that if f prime is positive, we say that f is increasing. And if f prime is negative, we say f is decreasing. And if f prime is 0, check out my last video, but you have a potential max, min, or neither. There was some criteria for all of those. So similarly, f double prime, so if f is the same function we're talking about, any function, f double prime of x will tell us about the concavity. So how does it do it? Here we go. If so let's just say let f of x be a function, then if f double prime of x is positive, then f is concave up. If f double prime of x is negative, then f of x is concave down. Now remember, it's telling you something about these at a certain point, and we're going to extend that to an interval and sometimes the whole function. But again, when you think about sine or cosine or polynomial, a lot of times it will switch concavity. And then the last case is if the second derivative is 0, and try to make analogies with kind of this stuff up here. If f double prime of x is 0, then you have a potential point of inflection. Sometimes this is abbreviated POI because mathematicians are lazy. No, we're efficient. So POI, point of inflection. All right, let's just look at a couple classic functions and kind of explain this with those. So let's just start very quickly with y equals x cubed. All right, we know visually that this looks like this. So, very quickly, the first derivative is this, and the second derivative is this. So, just the algebra alone, if you set the second derivative equal to 0 and solve for x, what this is saying right here is x equals 0 is a potential point of inflection. And because we know the graph, we can verify it. This right here, whoop, is concave down. And this right here is concave up, the curvature. Again, curve, concave up, concave down. So right there at the origin is a point of inflection. We verified it essentially with the graph. Also, just to recap my last video, if you set the first derivative equal to 0, you would also get x equals 0. Lots happening at 0. But this picture is not a max or min. Even though the first derivative is 0, it's not a max or min because the slope didn't change. Positive slope, 0 slope, positive slope. There's a special name. It's unique. We call that a plateau. So again, we're reviewing some of the other concepts. All right, let me add another page. Here we go. We're adding a page. All right, let's look at another one. I don't want this video to get cut short. Let's look at a couple other. Here's another classic. We know that the first and the second derivative of e to the x is e to the x. We know the graph looks like this. Boom. So what do we know just looking at the graph? Well, a couple things. This slope, boom, is always positive. So if you tried to find a max or min, set the derivative equal to 0. Doesn't happen. You can't solve this. It's never equal to 0. That's why we can say no max or min. Second derivative, is it equal to 0? Nope. So there's no point of inflection. All right, another quick graph. You got to be careful with some of these. I'll try to cram some of these in here in a few minutes. YouTube limits the length of my videos. I know you wish they could go on forever. Okay, f of x equals x. The first derivative, boom, is 1. Second derivative is 0. Here's where you got to be careful. Because the first derivative is 1, 1 is always positive. And what that means is the graph is always increasing. We're using the signs to make conclusions about f. Again, we're making conclusions about this. F double prime right here is 0. What does that tell us? It tells us we have a potential point of inflection, but it is not a point of inflection because lines don't have concavity. So it's almost just like extra information. It is not a point of inflection. Because it doesn't change concavity. Doesn't change concavity. All right, last example. Here we go. So more commonly, and I'm making up a function, we'll see how it plays out. But if you have like x cubed plus 2x squared minus x plus 5. And you're asked about the concavity, or the point of inflection, or the maxes, or the mins. What you're going to end up doing is taking derivatives very quickly. Again, this is nice because it's all power rules. So that's the first derivative. Second derivative is 6x plus 4. All right. So if you set the second derivative equal to 0, you very quickly get xe's negative 2/3. This, according to today's lesson, is a potential point of inflection. I don't want to graph it, but I want to verify, is it actually a point of inflection? So I mentioned it last time at the end of my video. Same thing here. What we can do is a quick number line graph. And if I think of, 0, and I think of, I'll just go this way, negative 2/3, and I think of negative 1. And I substitute negative 2/3 into f double prime, well, I know that that should be 0. And if I substitute 0 into f double prime, 6 times 0, I'm doing this up here, I know I'm moving quick, this is positive. But if I plug in negative 1 into that, I get negative 6, I get negative 2. Oh, what does this tell us? Well, it tells me that my concavity to the left of negative 2/3, this concavity is concave up. But this negative tells me it's concave down, and this 0 tells me there is a point of inflection because the concavity changed. We can use the values around this value to determine if it's a point of inflection if the concavity changes. All right, I'll leave you with that to think about. I'm going to stop this for now just to be safe on time, but I appreciate you watching. Hopefully this was a little bit insightful.